Welcome to This Explainer. Today, we are tackling the absolute beast that is Calculus 2. If you're looking to cut through all the noise and finally master this notoriously difficult subject, you are in exactly the right place. We're using direct source materials, everything from super strict professor prefaces to incredibly handy university cheat sheets to build your ultimate survival guide. We're going to visualize the core concepts that trip up so many students, turning what feels like a mathematical gauntlet into a clear, manageable path to understanding.
Here is our game plan for the day. We'll be covering rules of the game, approximating the world, shaping space, heavy lifting, and lastly, the infinite challenge. Let's get right to it.
First up, the rules of the game, or as I like to call it, surviving your professor's syllabus.
Right out of the gate, the professor sets the tone with his brilliantly snarky critique of elite universities, drawn straight from his preface. He's referencing a former Yale professor's critique of American education, just to remind us that we need to check our egos at the door. Basically, exam problems aren't just going to be copy-pasted from your textbook. You really need genuine intellectual independence here. There's absolutely no coasting allowed. Expect total novelty on the exams.
And along with that attitude comes incredibly strict rules on mathematical grammar. As you can see, the argument of a function absolutely must be in parentheses, no exceptions. If you write sine of x squared without those parentheses, you're leaving a lot of room for ambiguity. The professor makes it crystal clear, if you mean the sine of x and then you want to square that whole thing, you have to write it out meticulously. In Calc 2, precision isn't just a nice-to-have, it is quite literally a survival requirement.
Moving on to Part 2, approximating the world and how we actually measure reality.
So when we're dealing with sweeping, complex curves like this cubic function, basic geometry just doesn't cut it for finding the area between x equals 1 and 4. We actually have to approximate it. We do this by slicing the area up into subintervals and using rectangles, Riemann sums. By picking sample points like the midpoints of the rectangle bases, we can start piecing together an incredibly accurate estimate of that total area.
Now, the crazy thing is, depending on the exact sample points we choose within those intervals, we fundamentally change our approximation. Choose the highest points in each segment, boom, you've got an upper Riemann sum, which acts as a strict overestimate of the true integral. Pick the lowest points, that gives you a lower Riemann sum, a guaranteed underestimate. Figuring out how to bound your integral between these two extremes is absolutely crucial.
But hey, you're probably wondering, when do we actually use these approximations in the real world? Are we just going to spend all semester measuring abstract curves?
Well, the answer is literally all around us. This right here is the net change theorem in action. Just look at this graph tracking the electric power in megawatts used in San Francisco over a full 24-hour period. By finding the area under this curve using an integral, we aren't just doing some abstract geometry puzzle, we're calculating the massive megawatt hours of actual electricity consumed by an entire major city in a day. It takes the abstract math and plugs it directly into the physical energy grid.
All right, Section 3, shaping space. Let's take things from 2D into 3D. Here's where things get really cool. We're transitioning from integrating flat, two-dimensional areas to calculating the volume of massive physical objects. Take a look at this 16-foot semi-cylindrical water tank. By taking an infinite number of 2D cross-sections and adding them all up using an integral, we can perfectly determine exactly how much water this entire 3D structure holds. We rotate, we slice, and we integrate to literally shape space.
Next up is Section 4, Heavy Lifting. We're diving into the physics of calculus. This is where calculus starts doing the real heavy lifting for physical problems. Integrals are your go-to tool for calculating work, which, remember, is just force applied over a distance. But what happens when that force is constantly changing as you move? That's where calculus swoops in. We use integrals to find the exact joules needed for some pretty brutal tasks. Think stretching springs with specific constants, pumping thousands of liters of water out of swimming pools, or hauling incredibly heavy chains up the side of a skyscraper.
To put that into perspective, just look at the sheer scale of this specific problem from our source material. Imagine lifting a massive 300-kilogram load 24 meters into the air, using a cable that itself weighs 220 newtons per meter. This is a brilliant problem because as you pull that load up, the amount of cable hanging down is shrinking, which means the weight you're pulling is constantly getting lighter. You actually have to combine the static weight of the object and the variable weight of that shortening cable into one complex integral to find the total work done. It's wild. Finally, we arrive at Section 5, the infinite challenge. Time to master series. So we have officially reached the final boss of Calc 2, infinite series.
This is all about adding up an infinite number of terms and trying to figure out if they converge to a nice finite number or just spiral completely out of control into infinity. This table from the California State University's San Marcos cheat sheet is essentially your ultimate arsenal of weapons for this. When you're staring down an infinite series, you gotta know which tool to grab. Is it written as 1 over n to the power of p? Boom, p-series test. Does it have messy factorials in it? The ratio test is your best friend. Flipping back and forth between positive and negative, go straight for the alternating series test. Memorizing when to deploy which test is literally half the battle won.
And according to the source, your absolute best strategy is to always make step 1 the test for divergence. You just take the limit of your sequence as it approaches infinity. If that limit doesn't equal 0, well, congratulations. You get to immediately say the series diverges and save yourself from doing any extra complicated work. But watch out for step 2. If the limit does equal 0, the test completely fails. It tells you absolutely nothing, and you gotta go right back to your arsenal and pick a different method.
But, as the cheat sheet helpfully reminds us, these are just suggestions. There really isn't just one rigid path to the right answer here. A limit comparison test might work just as perfectly as an integral test for a specific problem. Multiple mathematical tests can lead you to the exact same valid conclusion. It's really all about finding the path that clicks for you.
Which leaves us with one final thought. We've gone through the strict notation rules, the real-world approximations, and the tools you need to literally tame infinity itself. Calculus 2 isn't just some arbitrary hurdle they put in the way of your engineering degree. It is the fundamental code for how our entire dynamic universe operates. So the real question is, are you ready to speak the language?